what capstone project he might want to undertake. And I asked him, what do you want to do after you get your degree? And he said to become a teacher. So I said, well, let's do something in the classroom, giving you some experience there. We were in my office yesterday joking that the tagline for this project should really be, oh, that took longer than I thought. But as it often does with teaching. But nonetheless, Zach did put in the time and has developed several activities that we've already used some of, and I'm looking forward to actually using in my classrooms in the future. So with that said, let's welcome our speaker, Zachariah.
Thank you, Dr. Target. As he just said, I'm Zachariah Miller, and I've been working on instructional development and evolution of material and self. Creation of material for students and what it takes to develop successful material. A little background before I go into what I did. The course in focus here was Astronomy 231. It is an introductory astronomy laboratory that is associated with the introductory astronomy course A100 offered here at Sonoma State University. Throughout the lab, students are going to be faced with some of the topics you see here: photometry, spectroscopy, measuring astronomical distances, dealing with those types of magnitudes, and even just down to basic mathematical processes that you will need, to go through a laboratory like this. I actually had the experience of going through the laboratory myself a couple of years ago, and I can say it's a very crucial turning point for anyone interested in pursuing a career in physics or astronomy. It's where you first realize astronomy is a very technical science. It's not just pretty pictures and swirling galaxies. But with that said, even if you're not interested in a career, it's just a very cool experience. For me, it was the first time I was able to go out and use a telescope and observe the night sky. I saw a binary star system, and to the naked eye, it was a single point of light in the sky. Through the telescope, it turned into two, and that was a very cool, enlightening experience for me. So within the lab, students will work through about 12 different laboratory exercises, and what I focused on was remodeling and redesigning 3 of them. 2 were observation labs, where we would actually take the students out to the SSU observatory and give them a chance to work with telescopes and draw constellations, observe how those constellations may move in the sky, taking down different information about star magnitudes, limiting magnitudes, things of that sort. However, the bulk of my presentation here is actually going to focus on the scientific methods and mathematical processes lab. There's a picture of the front there. So this laboratory, it's an introductory assessment. The students are coming into this lab environment for the first time, and there's a certain set of skills that are necessary for success in the laboratory. Those skills being SI units and their prefixes, essential algebra, scientific notation, significant figures, graphs, comprehension with graphs, maps, and understanding uncertainty in the data that they produce. So the reason we're redesigning this laboratory here is because Dr. Target started noticing a pattern in his students. They would go through this assessment laboratory, they would do the work, they would follow the instructions, they would get a good grade, and they would move on. However, later in the semester, he was discovering that students were still unable to exemplify these skills that they needed to do. They were not able to realize significance in an appropriate situation. They were unable to deal with scientific notations, very large numbers that are often encountered in an astronomy laboratory. And so we set about trying to fix this, and gave me a chance to brainstorm on exactly what was going on. Why were these students being successful in the first place doing the lab, but then not able to perform at a later date? And it brought me back to my experience with Dr. Hahn back here in one of her classes a couple years ago. And anybody who's gone through a course with Dr. Hahn knows she's all about her catchphrases. She will shout these catchphrases throughout the entirety of the course and make sure by the end of it that you're leaving with them strongly ingrained in your head. And the one big one that stuck was monkey see, monkey do. Every time she was handing out these papers and worksheets, you know, monkey see, monkey do, class. And at first it's like, why is my professor calling me a monkey? But it started to stick. It's what happens when you give students these worksheets is by now they've learned how to play what I call the game of school. They can fill in the blanks, they can follow a set of instructions, and they can turn that in for the grade they need, and then they move on. And that's all they really get out of it. And so what Dr. Hahn was always trying to say with monkey see, monkey do, which turned out to be probably one of the most influential pieces of advice I've ever gotten in my education, was don't just go through the motions. Understand why you're learning something. Be able to comprehend the reason behind what you're learning. And so that right there is the key piece of core philosophy that I began to redesign this laboratory with. To prevent the monkey see, monkey do at all costs, to help the students find the reason why they're learning something. And we went about doing that by following a couple key things here. Provide problems on relatable terms for the students, and to taper the problems from, say, a more relatable situation to something a little more difficult, something you may encounter in astronomy. So the first example of that is right here with significant figures. Very important concept to understand when working with anything in science. And it comes with a very explicit set of rules. You have your data that you work with to get your final answer. You go down these set of rules. They tell you, okay, this is what you used to procure this data, and now this is the amount of significance you're going to want to apply to that final piece of data. And students can follow those sets of rules, but what I saw it doing was provoking the monkey see, monkey do syndrome. So we set about solving that by offering a couple example problems here that would first get the students to realize one important key concept. They already know significance. As you can see here, this problem here involves asking a fellow student for the time, and he only has an atomic clock to check, which is accurate to 10 or so decimal places. And instantly that student's going to realize that's unnecessary information. They're going to round it to 3:45, say even 4 o'clock, and that gets the message of significance across. Same thing they're encountering here, looking up map distances from Sonoma State and to New York, and you get this decimal place answer, but really when you're going to reply to your friend, you're going to say 3,000 miles away, something along those lines. And so by exemplifying that, the students are now able to take the same concepts they're using right here and apply it to a situation that's a little more difficult to understand, maybe a situation that you're going to encounter when dealing with things at an astronomical size or distance. They're going to see here that their final answer is as accurate to the hundredth place there, but in your final answer, dealing with a distance that large, the students should now realize the insignificance of a fraction of a meter at the end of that. 150 billion meters is going to get the message across, and that's what we're looking for the students to figure out there. Again, this is now another section here dealing with unit conversions, and we are again trying to follow that core philosophy there. Taper from simple conversions up to a more relatable multi-step conversion where the students are going to realize that what they're doing has importance. There's a reason for putting the students through a multi-step problem like this. We're going to give them information about dosages at certain time frames. You're going to be looking at the weight of those dosages, and then essentially you're asking the student, what is Calvin here going to have to resupply or not? And so it gets the students to take all these moving pieces and parts and simple unit conversions that they had just done in the previous examples, and now combine all that in an effort to utilize that in a more real life situation. This is the problem, the following problem. It's the same type of situation. Joe here is from Canada. He wants to take a road trip down the coast of California. However, he needs to basically make sure all his finances are in order, dealing with financial currency exchange rates, dealing with mileage, gas efficiency, and how much that gas is going to cost. In a sense, overall, we're trying to get the student to walk away with an encounterable situation, something that they can relate to their own lives, where you're going to be taking a road trip, you're going to deal with these same types of exercises, just not so much in a laboratory format. And so what happens, or my hope, is that the students are going to be walking away with an idea as to why these unit conversions are important, why they should be being taught this material, not necessarily just how. How is less important. Anyone can Google search how to convert units, but what we want the students to walk away with here is an understanding of why they're doing this. So with the philosophy accomplished, it was time to administer the packet that I had created, and it would be my first experience up in front of a classroom and dealing with students. To set the stage, the classroom here consisted of 24 students. They were divided into groups of 2, and each one was given a lab packet that they could work with. And before I was moving into it, I had a mix of excitement and intimidation. On one side, it was my first time creating tangible material. It was like a piece of art that I had come up with myself. Each of these problems, I had poured a lot of time into making sure that the students were going to respond to them in the way that in a way that's engaging, and to where they're going to want to be taking away the why are we doing this. It was an opportunity to practice the goals I see for myself as a teacher: community, enthusiasm, and passion. And I'm in charge of molding minds. What's more exciting than that? However, on the flip side, my age. All these students are only a few years younger than me, if not my age, and I'm very concerned about if they were even going to do my work. And then even further beyond that, will I even be able to help? Is this packet here going to be beneficial to the students? And if all else fails, at least I had Dr. Target's stern face behind me, keeping them in line. Turns out, though, that most of these were just irrational fears, and the students took very well to the material I presented to them. There's certain students that struggled, certain students that did well with it, but the best part was seeing those students struggle with it at first, maybe a little reluctant to start those long word problems, but in grading and after the matter, they took well to it. A lot of students had shown success even in the hardest of problems that I created for them. We looked at student scores. We looked at 3 laboratories after the administration of this mathematics processing labs, and we noticed close to 10% increase in those scores. We looked 2 semesters back, and there was a noticeable increase in student scores from this semester that we had given it compared to the previous 2. And not only that, but a more frequent usage of the skills, such as significant figures, the scientific notation, and unit conversions. I would like to thank Sonoma State University faculty and staff, SSU Physics and Astronomy Department, all the classmates and my peers for their support, the students of that Astronomy 231 for coping with me, and Dr. Target especially for the support, and then friends and family, of course, couldn't have done it without them. I would like to end on one final quote here, one that was important to me growing up. With great power comes great responsibility, by Ben Parker. I finally think I truly know what that means. To be responsible for shaping and forming the minds of future generations, that to me is real power. Thank you.